Alright, in this video we'll continue where we left off last time, and we'll take a look at the A-star algorithm, search algorithm. Last time we implemented Dijkstra, so let's have a look at how that works. So we can do something like this. Let's make a start and an endpoint, and we can draw some walls, maybe like this. And if we run the search algorithm, it will gradually search around this little grid world, and eventually it will find the goal, and we can reconstruct one option for the shortest path. Now I made it symmetrical, so another option is going this way. We can try to see that by doing it like this and running it, and now the shortest path is this way. All right, so with that in mind, let's have a look at an algorithm that usually will find the path going from start to finish faster, if not always. And that algorithm is A-star. So I have the Wikipedia page here, which we will kind of follow. But the core idea of A-star is that you have for each point, so let's say this one, you can calculate a guess as to the distance between that point and the goal. And for A-star to work, that guess has to be optimistic, meaning that the actual distance has to be greater than, equal to or greater than the guess you make. So let's see how that works. Let's start by defining that guess, I suppose. Yeah, let's do that. So could be an inline function, so we'll call it heuristic, and it will be a function that takes 2 points and returns a distance. And right now we'll just use the Euclidean distance. That is kind of like the distance if we could go directly in a straight line. In this kind of grid world, we have to go either, north, east, south, or west. But suppose we could go straight. Now that's clearly like an optimistic guess, because you kind of like skip a lot of things if you do that. So let's see about that. So the Euclidean distance, let's do it like this. It is the difference in the x-coordinates squared. So let's actually do it like this: x squared, or the difference in x squared and the difference in y squared. And let's do dx squared plus dy squared. So we will need the math library. But now we have the heuristic. So the idea is that you have searched a bunch of points, and then you keep track of a list of points that you want to check, and the next one you check is the one that, as far as you can tell with your guess, is the closest to the target. So it makes a lot of sense, I think. So we need this concept here. They call it an open set, but this is like the points of the points that we want to look at next. So let's go here, and let's say before we had unvisited, now we're gonna add point list that we'll call just the open set. And beyond that, we also need here they have something they call G-score, which is what we call distances before, and they also have something called F-score, which is a current best guess as to the distance between the starting point and the end point, whereas this was just from the starting point and the current point. Yeah, so this is like the best guess for going from start to end if you pass through whatever point we're currently talking about. So maybe we can call those not G-scores, but because I cannot think of anything else, we'll call it F scores. And this will be for A star, this is G scores, and for A star, and this one is also for A star. All right, so let's have a look at this. This came from, we don't need, that is basically the path. And now we've added two things. So when we reset the world, or rather initialize the world, we should also, let's say, initialize A star stuff. And why is it doing this? Something is wrong. Let's try this. So reset world. And okay, now, so just had a bit of a breakdown here. Okay, so the F scores we also need to set to something. So let's do this. We'll just loop over all the points. And so if the default value is infinity, so we got that here, that's the default. And if we're equal to the start point, then it should be the heuristic, the guess. So let's add that here. Heuristic from start, which is the current point, to the end point. Okay, so those were the two new things. Let's now also go to the main function, and let's set that stuff up. So we need another point list, which is the open set. And we can let Copilot fill that out. Then we need the F scores, which we can put like that. And then let's add it here, open set and F scores. Right, let's check that it compiles. It still compiles, and it seems to run. Let's now add a mode. Let's add a mode, and I'll just have it up here as like some kind of global variable. So let's say, let's call it A star is active. It will be true by default for now, because this is what we want to work on. And now here in the step function, if A star is active, then we'll do one thing, and otherwise we'll do another thing. And what we will do is do a step of A star on the world. So it's going to be a function very similar to this step Dijkstra, but with a different name. So I believe this is step Dijkstra, so let's put it below here. Step A star. We take a world and we do some stuff. So let's have a look. We will kind of assume that it's already so the current, when we reset the world, the current is of course the start, because everything else is this is not the reset world. Reset world. Where are you? Here you are. The current is always the start, which is correct enough. And so we'll assume that whenever we enter this function, the current is the node in the open set having the lowest F score value. But that means that when we exit this function, we should, let's say before exit, update current to be the point in the open set with the lowest F score. And we do it at the end because we kind of have a slightly different structure than this this pseudocode, because we want to do an animation. All right. Now we'll have some kind of, we'll need some kind of like a termination condition. We have already seen the end, but let's hold off on that. So first we should remove the current point from the open set. And remember, the open set is this set of points that we should still try to investigate. So let's say list remove from the open set, remove the current one. So I don't believe we implemented this last time. Indeed we didn't, but let's go to point list and let's say list remove, and it will take a pointless pointer and a point, and then we'll loop through all the points in the list. If x and y both equal what we found, then we'll move everything above that one down. We'll say it's true, we'll decrement list, and we'll break, and we will assert that we actually found it. Okay, so all of that was very quick to make with Copilot, which is nice. So now we need to loop over each neighbor of the current. So for that we can just grab this that we made before. We consider differences of x and y, and if the differences are both 0, then we haven't really moved, so we just skip that. If they are both not 0, then we also skip that, because that's kind of like a diagonal point, and we don't include that right now. Then we construct the neighbor, we check that the neighbor's within the world, we check that it's unvisited. This one we actually don't need. And if there is a wall there, it's actually not a real true neighbor, so we also skip that. Okay, so let's have the current distance, what they call G-score, which is the distance to the current plus distance between current and neighbor. So I'm just putting this very explicitly because I want to make a point, and that is that this is always 1 in this world we have here. You could consider a different type of world where it's not always 1. For example, if there's like swampland or something, then it's harder to go through there. But for this simple world, it's just 1. Now, that means that going, as far as we can tell, going from the start to the current point, and then going from the current point to this neighbor that we're considering now, that is this distance. Okay, so if the current distance is smaller than the distance that we have so far recorded at the neighbor, then we are in here. We need to do some stuff. This guy we ignore, and then we update this score. Okay, so set distance at world neighbor current distance, and we should also update the F score. So we should say that, well, let's calculate the F score. I do agree with that. So it's the current distance, as we have here, current distance plus the heuristic plus heuristic. So let's say set F score at the neighbor to this value, and if this neighbor is not in the open set, we actually add it. So if not list contains world open set, then we add it to that. Okay, we have this function that we need to implement. So let's go to distance at, and down here we'll say static inline float. This thing should actually be void. Sorry, not distance at, but F score at. And the same thing with set F score at. So these are basically copy pastes of these functions. We could even make a macro if we want it to be extra confusing, but Copilot lets us handle it quite easily. All right, so now everything here should be Fine, let's try to compile it. It still compiles. So now let us do this thing, this finish condition. So we should find the point that has the lowest f-score. We do that by this standard minimization thing, where we loop over all the points in the open set. We find this f-score, and we find the lowest f-score. Then we set the current to that point. Now, when do we terminate? So that's a good question. So here we terminate if the current is equal to the goal. So I guess that should work. So if world current is equal to the end, we just finish. So that was a lot of coding. Let's see if it works. But the core idea is that we have a list of points that we want to check. Once we check a point, we check all the neighbors of that point, and we calculate the best guess from going to that neighbor and then to the end, which is this f-score. And then for the next point, we choose the one that has the best, like from our guess, it is closest to the goal. And that's very nice because it will fail on an assertion. So let me just debug that. Okay, so I believe the problem was in here because we forgot to add the starting point to the open set. Now, if we run it, it doesn't crash, but it also doesn't show anything. And the reason for that is that our draw function here, it relies on points being in this unvisited thing. So we should also here, I think, let's remove from the unvisited set this current point. Now we can step through like this. And you can see it's not doing something particularly smart, and it's actually not even going all the way to the end. Let me debug that. All right, so I've added this little statement here that if we ever meet the neighbor, if we ever meet the endpoint, then we set the current to that point. We record the distance, and then we basically return because we are done searching. So in this variant of A star, we just stop as soon as we have found the endpoint. So let's see how it looks. So it looks like this. And now something that would be nice to do is to be able to switch which one we have active so we can compare them. Let's go to the main function and let's say if is key released, key M. We're going to toggle A star active, and then we should also have a little rectangle here that is, let's call it an info box, and I think we have a function for that. Let's say top left. Yeah, so rect top left of the window, and the width can be everything, and the height can be whatever's left over from the center. And then down here, let's draw the info box. And let's not do that. So let's have it near the other draw function. So draw info box, and it takes a rectangle location. And what are we going to draw? We're going to draw which mode is active. So let's have here the text, and if a star is active, then we'll say let's do something like this. And then let's just say, what is the font size? Probably 20 is good. And what is the width? And then let's draw it centered in this rectangle. So let's have a look at that. That did not really work, which means that there is a problem with this info box. Let me try this. Right, because each side is 10%. And now we can change it between Dijkstra and A star, so we can compare them. So let's have a look at this. Okay, it just does this very silly search where it gradually expands like this. How does Dijkstra do it? It does something quite similar. But it goes in this diagonal pattern where A star went in this kind of rectangular pattern almost. But let's have a look at another case, this case. Here A star is quite good. It just goes basically directly to the goal. And if we reset and we switch to Dijkstra, we can see that Dijkstra wastes a lot of time searching all sorts of stuff that if you had a better idea about which direction to go, then you wouldn't need to search all this. And this is exactly the point of A star, that you have an idea of the direction to go. In the original case, why does A star behave so weird? That is actually a result of having this rectangular world where we can only go north, east, south, or west. If we can also go along the diagonal, it looks a bit different. So let's try to add that, and it's actually as simple as commenting out this line. So now we can go along the diagonal. Let's see how that works. Now it knows that this one is closer than these points, so it checks that one first, and then it basically continues like that, and you can see it just goes straight for the goal. But just for the purposes of this this video, we are not going to consider this diagonal movement. Let's try a little bit of a bigger world, and let's add some obstacles. So for example, try something like this. So again, well, now we need to change the font size. And where did we have that? Font size, it's just in here, so let's say default font size. Sorry, it's a bit hard to read. And the same here. The info box doesn't need to change, actually could even be a bit bigger. But let's go up here and say default font size is 20. But then we'll also set it here where we actually change the size of the world. So this stuff up here is quite a bit bigger, but let's see if we can actually see the numbers, and we can. Okay, let's try to make this kind of obstacles again, and maybe there's also like a room like that. So let's see how A star does. It again tries something. It's not particularly impressive, but it is a tricky case. So now it found a path, and we'll see. We can try to reconstruct the path and see that it actually is this fastest path. So it tried a lot of stuff. We can try to run it again. You see, it kind of made this sort of rectangular area that it ended up checking. So let's see how Dijkstra does. And you can see it's almost like this wavefront that's spreading out, and it ends up checking a huge amount of stuff. So we can make it even easier for A star, like that. And we can try Dijkstra again. It basically does the same. It has no idea about what to expect. So let us try just another simple example. Here, this one is quite good, and this one is always the same. The most striking, of course, is if we do something like this, just have a straight line. Dijkstra, A star goes directly for the goal, but Dijkstra does all this crazy stuff. I think when we change the mode, we should also just reset the world for convenience, so that we can do like this. It's one fewer key press for me. So that does it for this video. And you can play around with this forever and see how things change as you change the world. So that's it. I hope you liked it, and I will see you in the next one. Bye bye.